Welcome once more to another video in our YouTube channel. So in today's video we are going to be looking at further complex numbers. So this video is specifically for those who are in the university, those who want to write entrance examinations into professional schools like Polytechnic Yaoundé, Polytechnic Douala, those who are in the advanced level and offer further mathematics, and teachers as well. So if you're offering mathematics, you can watch the video, yes, but it's not too important for you, though there are some important concepts that will be explained, which you need those concepts. So don't think you're wasting your time in watching this video. So this question was proposed to me by a student who is in upper seed at St. Benedict's College in Yaoundé. Alright, so for those of you who are just joining us for your first time, endeavor to subscribe to the channel, turn on your notifications after subscription so that whenever videos are being uploaded, you'll be notified to come and watch. Like the video, share the video with your friends, comment, and stay tuned. Alright, so let's get started. So the question reads, the question is divided into 3 parts and we are going to solve the parts independently. 1. Given that omega is equal to cos theta plus I sin theta, find the modulus and the argument of omega. Okay, so let's begin with that. So first we need to find the complex number 1 plus omega first, right? So after getting 1 plus omega, before we see how we can get the modulus and the argument. Okay, so omega being equal to 1 plus cos theta, we can get 1 plus omega as 1 plus cos theta plus I sin theta. So what I did was that I just paired already the real part of the complex number 1 plus omega, which is 1 plus cos theta, and the imaginary part. The real part is what is not attached to I, and the imaginary part is what is attached to I. So the imaginary part is sin theta and the real part is 1 plus cos theta. Alright, so the modulus of the complex number is just the length that the complex number makes. That's the distance from the origin to the affix, or the point of that complex number in the Argand diagram. Okay, so 1 plus omega, her modulus is just given by the modulus of 1 plus cos theta plus I sin theta. And how do we get it? We take the square root of the sum of the squares of the real part and the imaginary part. So the real part is 1 plus cos theta. We need to square it. We add it to the square of the imaginary part. Then we take the square root. Now let us expand 1 plus cos theta all squared. We are going to get 1 plus 2 cos theta plus cos square theta. Now we need to add sin square theta to it. So we know the identity cos square theta plus sin square theta is equal to 1. So it means this add up to give 1, plus this one here we get 2. So it means that this modulus simplifies to 2 plus 2 cos theta. But we can't allow our answer here like this. It's bizarre to have the modulus in square root forms if there is a possibility of us simplifying. So let's go ahead and simplify. Now we use the basic identity cos 2 theta is equal to 2 cos square theta minus 1. So I can have the angle, meaning that I divide 2 theta by 2 and I divide theta by 2. So it means cos 2 theta on 2 will give me 2 cos square theta on 2 minus 1. But cos 2 theta on 2 is cos theta, and theta on 2 is theta on 2. So it means cos theta is 2 cos square theta on 2 minus 1. Now I come back and I fit in the place of cos theta as 2 cos square theta on 2 minus 1. I multiply all through with the 2. 2 times 2 cos square theta on 2 is 4 cos square theta on 2. 2 times negative 1 is negative 2. Now 2 minus 2 is 0, so at the end we get 4 cos square theta on 2. The square root of 4 is 2, and the square root of cos square theta on 2 is the absolute value of cos theta on 2. It is not cos theta on 2, please. It's the absolute value of cos theta on 2. Now we need to verify if the absolute value of cos theta on 2 is cos theta on 2 or it is negative cos theta on 2. Alright, so I'm going to set cos theta on 2 to be f of theta. So it means cos theta on 2 will be either, so the absolute value of cos theta on 2, being f of theta, the absolute value of cos theta on 2 will either give me the cos theta on 2 provided it is positive, or you give me negative of it provided it is negative. Okay, now the argument of theta is actually the argument of the complex number omega, and we know the argument of the complex number lies between negative pi and pi. So with that we can get where theta on 2 lies by multiplying all through all through here by half, or dividing each quantity by 2. So dividing by 2 or multiplying by half, we get negative pi on 2 less than theta on 2 less than pi on 2. Now we are going to verify if theta on 2 is between negative pi on 2 and pi on 2, how is cos theta on 2? So we are going to see that graphically. So if I set alpha to be theta on 2, in my coordinate system, the vertical axis becomes cos alpha, which is actually cos theta on 2. The horizontal axis becomes theta on 2 or alpha. Alright, so alpha, theta on 2 lying between negative pi on 2 and pi. It means that alpha is between negative pi on 2 and pi on 2, sorry, because theta on 2 is my alpha. So I fit the coordinates. So you have pi on 2. So you have pi on 2 there. We have negative pi on 2. There we have 0. Now in the interval 0 to pi on 2, the cosine of alpha behaves this way. So here is the graph of cos alpha in this interval. So clearly it is greater than 0 because it is above the horizontal axis. Now in the interval negative pi on 2 to 0, that is also the graph, and it is greater than 0 because it is above the x-axis. So in essence, cos alpha is greater than 0 for all alpha in the interval negative pi on 2 to pi on 2. So it means that my f of theta is just cos theta on 2, sorry, because cos theta on 2 is positive, since cos alpha is positive and alpha is theta on 2. So it means that the modulus of my complex number 1 plus omega is 2 cos theta on 2, since the absolute value of cos theta on 2 is just cos theta on 2, because cos theta on 2 is positive. Alright, so the first challenge has been solved. Now we need to move on to the argument of our complex number 1 plus omega. Now what's the argument of a complex number? It's simply the angle that the complex number makes with a positive real axis. So it depends on the quadrant where the complex number lies. So the argument depends on the quadrant. If you're in the first quadrant, normal, second quadrant, pi minus the formula, third quadrant and fourth quadrant and all the rest. So for you to find the argument of a complex number, first you need to plot the complex number. Secondly, when you plot it, you identify the quadrant and then you use now the required formula. So if you're in the first quadrant, it means that the real part and the imaginary part are both positive. In the second quadrant, we have let me just try to indicate the quadrants here so you see clearly what I'm talking about. So though my diagram is not going to be very straight, but anyways, let's just say this is our Argand diagram. Horizontal is for real, vertical is for imaginary. Now this is the first quadrant here, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. I see that any point that is on this quadrant here, it means that the x coordinate, the y coordinate, which is the imaginary part, is positive, and the x coordinate is also positive. Now if I am in this quadrant here, then my y coordinate is still positive, but my x coordinate is now negative. If I am in this quadrant, you see that my x coordinate is negative, yes, but my y coordinate is also negative as well. So in the third quadrant, both real and imaginary coordinates are negative. But now in the fourth quadrant, we see that the x coordinate is positive and the y coordinate is negative. So for us to get the argument of our complex number 1 plus omega, we need to actually we need to know the signs of the real part and the sign of the imaginary part. We see that if we are here, if we are in the first quadrant, we just say tan inverse of the imaginary part of the real part. If you're here in the second quadrant, you need to take pi minus tan inverse of that quantity. In the third quadrant, you need to take pi plus tan inverse of that quantity. And in the fourth quadrant, you just take negative tan inverse of that quantity. So basically that's how the quadrants work. So in this case, we are just going to identify the quadrant where our complex number lies. Then from there, we can now compute the argument of the complex number depending on where it lies. Alright, so the argument of 1 plus omega is simply the argument of 1 plus cos theta plus I sin theta, because the interior here is 1 plus omega. Now this is the real part, 1 plus cos theta. This is the imaginary part, sin theta. We know theta is between negative pi and pi. So let's look for the sign of cos theta of 1 plus cos theta in that interval. So generally for any theta, for theta in this interval or in any interval, we already have -1 is always less than cos theta. So to get 1 plus cos theta, we add 1 on both sides. Left hand side is 0, right hand side is 1 plus cos theta. If 0 is less than 1 plus cos theta, it means that 1 plus cos theta is greater than 0. So it means that the real part of my complex number 1 plus omega is always positive, no matter where theta lies. Now, what about the imaginary part? We are going to plot on the diagram. So vertical axis for sine theta, horizontal axis for theta. Now, the theta lies between -pi right up to pi. In the interval 0 to pi, sine theta behaves like this, so sine theta is positive. In the interval -pi to 0, sine theta behaves like this, so sine theta is negative. So it means that the imaginary part has two signs. It is either positive when theta is in the interval 0 to pi, or negative if theta is in the interval -pi to 0. We have two cases, but generally the real part of my complex number is always positive no matter where theta lies, as we saw. The imaginary part will be positive if theta is in the interval 0 to pi, and negative if theta is in the interval -pi to 0. So with that, I'm still going to draw the quadrant system and then we identify our quadrants again. Okay, so vertical axis is for real part, horizontal axis for the imaginary, vertical axis for imaginary, so let me just call it IM, and then horizontal axis here is 0, horizontal axis is for the real part, RE. Okay, now for the first case, in all the cases the real part is positive, so it means that the real part is positive, so you're around here, right? Now first case for imaginary part is positive, it means that it is here, so it means we have the first quadrant for the first case. Now in the second case, the real part is still positive, but now the imaginary part is negative. Imaginary part being negative, it means that you're here, and the real part being positive, you have now the point here. So you see that our complex number either lies in the first quadrant or in the fourth quadrant. So we are going to use the respective formulas. So lying in the first quadrant, the argument is just tan inverse of the imaginary part on the real part. The imaginary part is sine theta, and the real part is 1 plus cos theta. Now, lying in the fourth quadrant, the argument is negative tan inverse of the imaginary part on the real part. It means in the first quadrant, we just have tan inverse of imaginary on real. Second quadrant, so let me just try to label this y. Let me label this -y. Now let me label this x. So in the first quadrant, our argument, if I call it maybe theta, is just equal to tan inverse of the imaginary part, so tan inverse of the imaginary part, which is y, divided by the real part, which is x. Okay, now in the fourth quadrant, my argument is just negative tan inverse of y divided by x still, so negative tan inverse of y divided by x. Okay, so we see that if we combine the two, because we were not given any condition here about theta, you see, so we can combine the two and then we get, because here this tan inverse of y on x is the same as tan inverse of y on x here, so we need to, here is positive and here is negative, so combining the two, that's why we get the plus or minus in front here. So we have plus or minus that. So that's how I did to get a plus or minus. All right, now we need to know the value of sine theta over 1 plus cos theta. All right, so we are going to use the half angle identity to know the sine, to know the exact value of sine theta divided by 1 plus cos theta. All right, so the half angle identity, when I say t, anywhere you see t, you know that it is tan theta on 2. So sine theta is 2t on 1 plus t squared, and cos theta is 1 minus t squared over 1 plus t squared. So it means 1 plus cos theta is 1 plus, here is cos theta. We can look for the LCM, we simplify and we get 1 plus cos theta to be 2 divided by 1 plus t squared. Now I need sine theta over 1 plus cos theta, so it is sine theta divided by 1 plus cos theta. Replacing the division sign with the multiplication, I need to invert the numerator and the denominator of the fraction you're dividing by. So the numerators can cancel. That's 1 plus t squared cancels with the denominator here, and 2 cancels as well. So at the end we get sine theta over 1 plus cos theta to be equal to t. But what is t? Is tan theta divided by 2. So in essence, our argument of 1 plus omega is plus or minus tan inverse of tan theta on 2, because this quantity here is just tan theta on 2. But tan inverse of tan theta on 2 is theta on 2. So it means that our argument is simply plus or minus theta divided by 2. Okay, so we have gotten the modulus successfully, and we have gotten the argument successfully. So now we are going to the second part of the equation. Just give me a few minutes to wipe out this. Alright, so the second part of the equation, we are asked to expand 1 plus omega raised to the power n, where n is a natural number in ascending powers of omega. So it is basically the binomial expansion of 1 plus of something raised to the power n. So here is it. I believe this is not difficult to understand. Even the formula book, you can find it. Okay, now the third part, we are now asked to show that the sum from r equals 0 to n of n factorial on n minus r, all that factorial times r factorial times the cosine of r theta, is equal to 2 raised to the power n cos raised to the power n of theta on 2 cos of n theta on 2. Okay, so follow keenly, because things become a little bit complicated here at the beginning, but now when we are going to be ending, you see how we took a very complicated question to a very, very simple question with the approach. Okay, so I'm going to replace the values of r, and we get the various terms and we sum them together. Okay, so when r is equal to 0, we get the first term, or we can say the 0th term. Replacing r to be 0 here, we have this. Replacing r to be 0, we get this, plus the second term, or the first term. If you call it the 0th term, then the first term. Replacing r to be 1, we get 1 here, and cos 1 theta is cos theta. Replacing r to be 2 to get the second term, we replace r to be 2 here, replace 2 here, then cos 2 theta. Right up till replacing r to be n, you get the n term. I'm going to show you guys what the n term is all about, what the n term is actually. Our n term is replacing r to be n, right? You replace r to be n here, this r becomes n. N minus n is 0, 0 factorial is 1. R becomes n, so this just becomes n factorial. Then numerator is n factorial, replace r to be n, we get cos n theta. That's why the last term is actually n factorial divided by n factorial times the cosine of n theta. Okay, so this now becomes, we can simplify n minus 0 is n. Then all that factorial, 0 factorial is 1, cos 0 remains cos 0. Now I'm going to write n factorial as n times n minus 1 all that factorial, and then that's divided with this denominator, then times cos theta. I'm going to write n factorial still as n into n minus 1 times n minus 2 factorial, then I divided with the denominator times cos 2 theta, right up till the n term. Alright, so this simplifies to n factorial is 1, cos 0 is 1. We get that, plus now the n minus 1 all factorial cancels with n minus 1 all factorial in the numerators. You're left with n times cos theta. Now here we have n minus 2 all factorial cancels with n minus 2 all factorial, and you're left with n into n minus 1 over 2 factorial times cos 2 theta, plus till the n term. Now remember, this is our n term. Anyways, our n term is cos n theta, because n factorial is 1. Now this one I'm going to do, I'm going to rewrite back this very sum that I have here till the n term, and then I'm going to do something special. What am I going to do? I'm going to add the imaginary parts of every term here excluding 1. So 1 is just going to be there. So I'm going to add up the imaginary part of n cos theta. I'm going to add up the imaginary part of this quantity, and I'm going to add up till the imaginary part of the n term. Now the imaginary part of n cos theta is in sin theta, right? The imaginary part of n into n minus 1 over 2 factorial times cos 2 theta is the same quantity but multiply with I and change the cos 2 theta to sin 2 theta, right up till you add the imaginary part of u of n, you get I times v of n. Now what is v of n? V of n is n factorial over n factorial times sin n theta. Basically it is sin n theta because u of n is cos n theta, so v of n is supposed to be sin n theta. But since we are adding the imaginary part, we need to attach an I to it. Okay, so with that said, we can now proceed. Look at what I've done. I've added the imaginary parts to this complex number. I've totally changed the equation, but this is not true if I allow it like this or if I proceed without doing something, because from this step here to this step here is not logical. Because if I'm adding the imaginary part to this complex number, I need to write down something that will make me to come back to this. So simply I need to write this as a real part of everything, right? Because the real part of everything here is just the terms without I, without the I attachment to them, and the only terms here without the I attachment to them is what is my previous step. So it means writing this previous step as a real part of everything here is correct, because the real part of everything here is simply the previous step. Now we now pair them, we now pair the terms together, the real parts and the imaginary parts. So I'm going to pair n cos theta with its imaginary part, which is in sin theta. We factor out the n, we get cos theta plus I sin theta. Next, I'm going to pair this quantity with its imaginary part, we get this. And finally, we are going to pair the n term with the imaginary part, so un plus ivn. Okay, now we are going to apply the De Moivre's theorem. So I'm just going to rewrite the first two terms. Now the De Moivre's theorem is saying that cos 2 theta plus I sin 2 theta can be written as cos theta plus I sin theta all that squared, meaning you take the 2 away from the theta and you raise everything raised to the power 2, right up till my u of n is cos n theta, my v of n is sin n theta, right? But since I'm adding cos n theta plus I sin n theta, applying the Moivre's theorem, I remove the n and I add both of them and I raise it to the power n. The same thing I did for 2 here. Alright, so now what can we see? We can see that cos theta plus I sin theta, what is it? Is omega. That was what was given to us originally. So we have n times omega. Now what about this cos theta plus I sin theta all squared? It's clearly omega squared because the interior is omega. So this is going to give us what? Omega raised to the power n. So we add till omega raised to the power n. Now let us see the relationship between this quantity here and our number 2. We see that they are exactly the same, right? That's the quantity in the box here and number 2 are the same. 1 is 1, omega n is n omega, this quantity is this quantity, right up till n factorial and n factorial is 1, so you end at omega raised to the power n. So that's where we see n. But now remember that we have the real part. So this sum here actually identifies what? It actually identifies a real part of this whole sum. But this whole sum is what? 1 plus omega raised to the power n. It means that this, our nasty sum here, is simply what? The real part of 1 plus omega raised to the power n. Because what is in the text box here is just 1 plus omega raised to the power n, but we need to attach a real part. So it means that our nasty sum is the real part of 1 plus omega raised to the power n. Things are now becoming very easy. Now a basic recall, if I have a complex number whose modulus is rho and argument is theta, then we can write it in the trigonometric form as z equal to r into cos theta plus I sin theta. Use that basic recall to see how we can manipulate to get a complex number 1 plus omega raised to the power n. Because remember, we need to get the real part of 1 plus omega raised to the power n. So if I take the first interval, that's when theta is positive, 1 plus omega is the modulus, which we found as 2 cos theta on 2. The argument, since theta is in a positive interval, we saw that the argument will be positive. Theta on 2 is the argument, so writing it in the trigonometric form, we have the modulus, which is 2 cos theta on 2, the cosine of the argument plus I sine the argument. The argument is theta on 2. Now for the second case, we just replace the argument with negative theta on 2. Okay, now what about 1 plus omega raised to the power n? It means we raise both sides. I'm just going to consider the first part. We raise both sides to the n, right? So raising this left hand side to the n, we get this. Raising the right hand side to the n, we get this. Okay, so we can now try to expand. So we have or use the Moivres theorem first. The n multiplies now the argument. So we have cos n theta on 2 plus I sine n theta on 2. Now we separate the real parts and the imaginary parts by multiplying each of them with the modulus. So we have the modulus times the real part plus I times the modulus times the imaginary part. Okay, so but what is this our sum? It was what? The real part, here is it, is a real part of 1 plus omega raised to the power n. And where is the real part? Let me indicate the real part in this color. So this is the real part, right? So this is a real part, which is this, and it is exactly what we are supposed to prove. So it means that our sum is equal to the real part of that. So replacing, we get a sum to be 2 raised to the power n cos raised to the power n of theta on 2 times the cosine of n theta. So basically that's what we are supposed to prove, and we have successfully proved it. So thank you for watching, guys, and see you in the next video.